Well, here we are, lesson 4 of the Carnival Tycoon project. We've already done 3 lessons, obviously, and had 1 assessment. You'll be happy to know that we only have 2 lessons left to go and 1 more assessment before we can start building our Carnival projects. And that should be a lot of fun. All right, but the information that we're learning is really useful for completing those projects successfully. So let's go ahead and look at the things that we're going to be doing in Lesson 4. So here we are at the Lesson 4 web page, and you can see it's labeled Probability Distributions. As always, we have the links at the top. Here's the video lecture that you're watching right now. Remember, you can always go back and watch pieces of this lecture over again to help you understand the concepts a little bit better if you need some review. Here's the link for the probability activities. We have the lecture notes here, which we'll be getting into in just a moment. We have Lesson 4 activity, and we have some reflection questions at the end, as always. And you can see that we have a review of some material right here, and it's not very long. It only goes on for 1 page. You'll recognize this picture a little bit later because we're going to be using it again, and some notes down here. I think you'll find that this lesson on probability distributions is one of the easier to understand, but it has a lot of very important information that will help you be successful in the project. So let's go ahead and start by having you take out your notes for Lesson 4 so we can get some important information down to get us rolling. All right, so here we are. We will start out by defining what discrete probability distributions actually means. So the word discrete actually means an exact or a finite value. So an example of that would be US paper currency, for instance. It's divided into discrete monetary values of $1, $2, even though you may not have seen a $2 bill. I used to collect these when I was a kid, $5, $10, and so forth. So there is no 1.2135 dollar bill, for instance, or a $5.311 bill. That does not exist. These are finite, discrete values, whole numbers in this case. Although they don't exactly have to be whole numbers to be discrete, but in this case, these are whole numbers. Now, what is a probability distribution? Well, if we do experiments in probability, we end up obviously getting results. So we have to present these results in some way, and it's usually visual. So this is a representation of data, usually visual, that shows the likelihood of all possible outcomes of a random variable in a chance experiment. So again, a representation of data, and it's usually visual, and it shows the likelihood of all possible outcomes of a random variable in a chance experiment. So it is theoretical. So what is a random variable? Well, a random variable is one that is determined by the outcome of a chance experiment. So for instance, if you are rolling a die, the chance that the random variable will be a 4, for instance, is 1 out of 6. Because there's 1 4 on that die, and there are 5 other possible outcomes, so it's 1 out of 6. But it could also end up being 1, 2, 3, 5, or even 6. So here is an example of a discrete probability distribution. So if we're taking 2 dice and we're rolling them and adding their values together, you'll notice that we get discrete values for our answers. You can get a 2, but the only way to get a 2 is by having one of the die roll as a 1 and the other one roll as a 1. Now you think, well, wait, I could get a 2, but you can't get a 2 because the other die doesn't have a 0 on it. It only has 1 through 6. So we can get a 2, but you'll notice there aren't very many chances to get a 2. It's only one possible outcome for getting a 2. But for 3s, notice there's a couple different outcomes for 3s. And for 4s, there's even more outcomes. But you'll notice that we cannot get a 4.5. That's impossible. because we're dealing with adding up two whole numbers. And then finally, when we get all the way to sevens, you'll notice that the 7 is the most likely outcome of adding the two dice together. And it goes right back down again. Getting two 6s is just as unlikely as getting two 1s. Only a 1 out of 36 chance of getting that to happen. So this is an example of discrete probability distribution. Another couple of examples that would be good would be like how many times hospital patients ring their buzzers for assistance during the night, for instance, or how many times mothers are awakened by newborns during the night. So you can't have 1.2 mothers being awakened by 3.12579 newborns during the night. So these are actual discrete values, discrete numbers. And what's important to understand is we're not talking about averages, because if we were talking about all the new mothers in Flint, Michigan, for instance, being awakened during the night by babies, on average, you could of course get a number that would be a decimal point, and it would be any value between, there are any possible numbers between 1 and 2, for instance. You could go as many decimal points as you would like. But for discrete probability distributions, we have numbers that are exact. So an example of something that would be non-discrete, we have a couple examples of those. So maybe you've seen the normal distribution that looks like this graph on the right. Some examples of this might be Michigan maple tree height. So if you take all of the maple trees in Michigan and you measure them, you wouldn't be actually measuring every single maple tree in Michigan. You'd have to do some kind of scientific sampling for that. But if you did that, you would find a whole bunch of these would be, somewhere around average height maple trees. You can see that bell-shaped curve. And some of them are smaller. Obviously, a smaller percentage of them are smaller, and a larger percentage of them are taller. It's important, again, to understand that we're not talking about averages, like the average of the maple trees. We're talking about actual maple tree height. So there could be any number of different heights between 50 feet 1 inch and 50 feet 2 inches. Remember, you could go as many decimal points as you would like, and since maple trees grow so slowly, then it could be any of those numbers. So these are not discrete values. Notice the gradual curve. That represents all possible numbers in the range. Another couple examples might be the eyelash length of chimps in Uganda, or the height of a population of males in Ohio. And a good example of this is also the visible spectrum of light. If you look down at the picture in the bottom left, you can see the Roy-G-Biv, the colors of the spectrum: red, orange, yellow, green, blue, indigo, and violet. And notice there is no distinct line between any of them. There's a blending of those lines and an infinite number of possible combinations of red and orange, or orange and yellow, or yellow and green, and whatnot. So these are non-discrete. So let's talk about the very practical example of flipping coins. We've used this example a number of times, and let's take 3 coins, for instance. Let's look at the results of flipping 3 coins. What are all the possible outcomes for the 3 flips? Well, it's pretty easy to write these down. Let's go ahead and record all the possible outcomes of flipping a coin 3 times, or 3 different coins once. We could get heads, 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 certainly could. We could get heads, heads, tails. We could get heads and then tails and then another head. We could get heads and then 2 tails. And then we could get tails, heads and heads. We could get tails, heads, tails. I have to write just a little bit smaller to get these on here. We could get tails, heads, and then finally, of course, we could get 3 tails, just like we got 3 heads earlier on. So what are these different, what do they represent? Well, this is clearly representing 3 heads. We'll look at this in terms of heads. 3 heads for this one. 2 heads for this one. Notice 2 heads for this one, although we rolled them in a different order this time around, but we did get 2 heads. This one we only got 1 head. This one again we got 2 heads. This one we got 1 head. This one we got 1 head. And this one we got 0 heads. 0. Okay. All right. So we're looking at what the likelihood of getting a certain number of heads is for this probability distribution. And here's how we record this. We call these outcomes. X, lowercase x. All of these different outcomes that we could get here. And what we're thinking about in probability is, what is the probability that our, what we call a random variable x, will equal lowercase x, all these different little outcomes that we have here. An outcome would be the total, or what the possibilities are. We could get 0 heads. We could get 1 head. We could get 2 heads. And we could get 3. That's it. Can't get more. Can't get less than 0. Can't get more than 3. All right, so we'll write this out in a small chart. And we'll record the data below. All right, for 0, how many zeros did we get? Well, we need to count that up. 0 heads. It looks like there were 8 total outcomes here, and there were only 1 that came up 0 heads. So 1 out of 8. And 1 out of 8 happens to be 0.125. And for the ones, looks like we have to count those up, see how many we had. We had 1, 2, 3 of those. So that turns out to be 3 out of 8, or 0.375. And let's count up the 2's. 1, 2, 3. So again, it's 3 out of 8 for 2's. And we already know that's 0.375. And finally, 3 heads. There is only 1 of those. So 1 out of 8, or 0.125. Let's make sure that we've counted everything up. There were 8 possible outcomes, and 1, 4, 7, 8. 8 results. Let's see what that would look like in a simple graph. See if I can write this on here for you so you can see it. So over here on the left-hand side of the graph, we'll go ahead and write the probability of x. And we'll do this in terms of percentage. That might be the best way to represent that on this one, in percentage. And we have some options at the bottom. 1 or 0, 1, 2, and 3. And if we look up at our scale, it looks like 37%, see, because this is 37.5%, if you remember, 37.5%, 12.5%, 12.5%, here is only going to be 12.5%. This one's going to be 37.5. Sorry, it's a little bit messy. 37.5% and 12.5%. So the highest percentage that we get in this graph is actually 37. So we could go up to 40% on our y-axis, 10, 20, 30, and 40. And this one here is just a little bit above 10. It's 12.5. And this one is almost up to 40, 37. So we're not being super precise here because we're just writing this down in our notes. If we had graph paper, we could do much better. We'll do the same here, 37.5%. Graphing this on here, and another 12.5. So you'll notice we have a probability distribution, and it's a discrete probability distribution with discrete values of 0, 1, 2, and 3. So there is nothing in between. There's no way to get anything in between those, so we don't have a gradual line like a normal distribution curve, but we have discrete values represented. All right, so we have an assignment that you're going to do, and you're going to be taking a basic scenario, and you're going to be taking the data out of that and making your own discrete probability distribution. So let me give you a look as to what this assignment is all about, and then I'll give you some directions. Okay, so lesson 4 activity on discrete probability distributions. This is what it's all about. It says you're creating a discrete probability distribution for a simple spinner game. Directions are you've been given a spinner disk that is subdivided into 3 equal sections. So you can see we've got a red section, a blue section, and a yellow section, and they are all equal. In the space below, calculate the probability distribution of all possible outcomes for 2 spins of the disk. Use data to complete the table as well as the graph. So right here, you're going to write all the different outcomes for 2 spins. And I will note that you could first spin and get blue and then get red, but the next time you spun it and recorded data, you could get red and then blue. Don't be tempted to think those are exactly the same thing for this assignment. Our y is different than YR because they came in different orders. So you'll write those all down here, and you'll write the fractions here. Then you are basically going to do what we did in the notes for the coin flipping, except you're using the spinner disk. You're going to compile the data and represent it as percentages on this graph down here and answer this basic question here. It should not take very long, probably 10 minutes to do this lesson 4 activity on probability distributions. Best of luck to you. You're going to see some directions up on the screen for you in case you need a review of what to do. But this is on the lesson plan page as lesson 4 activity, discrete probability distributions. Welcome back. I trust that you learned something in the probability distributions activity and that you can apply to your project. Speaking of your project, I want you to think about something for a second. You have probability distributions in any kind of experiment that involves random chance. And you know that there are greater likelihoods of getting some things and lesser likelihoods of getting other outcomes. Think about this in terms of carnival games, because if there is a greater chance, for instance, to get 7s when you take 2 dice and you roll them, we know that that's the greatest chance is you're going to get a 7. It's a relatively low chance, but it is much greater than getting 2 1s, for instance. Is that the one that you want to provide the most expensive prize for, or the least expensive prize? Because you have to start thinking in terms of profitability for the carnival, because this is what's going to take us into the next lesson on what's called expected value. Do you want to have a prize that costs the carnival $20, which would be really a massive prize actually, for a game that costs $1, and you give that $20 prize away to someone who actually picks a number that's the most likely number to get from rolling 2 dice? It's probably not the smartest thing to do. Remember, what you're actually shooting for here is you want to make the carnival some money, and yet it needs to be fun, so people need to be drawn to the game. So think about that as we move into the next lesson, which will be on what we call expected value, which really could be the most important lesson of the Carnival Tycoon project as we move forward. All right, that was pretty short. I told you it was going to be pretty short. We have lesson 4 reflections as the last thing that you need to do for this assignment, and you can find that on the lesson 4 webpage as always. And wish you the best of luck on the lesson 4 reflections. And I'll see you next time.